And you know what? Some shaking up there in Tahoe today, rattled by a quake this morning. And it was felt all the way down here in the valley and in Sacramento. A magnitude 4.2 quake hit right in the middle of the lake, experts say.
The gauge reads 6,229 feet above sea level. This is Lake Tahoe's absolute maximum legal capacity, the highest the lake is ever permitted to rise under a federal court decree established more than a century ago. Right now, billions of gallons of water press against that threshold with nowhere left to go. But beneath that impossibly blue surface lies the West Tahoe Fault, a massive 25-mile fracture capable of unleashing a magnitude 7.3 earthquake. This fault hasn't ruptured in approximately 4,000 years. Geological surveys indicate it's catastrophically overdue. The timing couldn't be worse. Maximum water weight on an overdue fault creates conditions seismologists recognize from disasters worldwide, and instruments surrounding the lake are detecting exactly what scientists feared: small tremors increasing in frequency, warning shots from a fault system under mounting stress. If the West Tahoe Fault ruptures while the lake sits at maximum capacity, the earthquake will only be the beginning. The real killer could be what follows: underwater landslides displacing billions of gallons, generating tsunamis that could strike shoreline communities in California and Nevada within minutes. Has the water that saved California from drought inadvertently created the perfect conditions for catastrophe? 5 years ago, Lake Tahoe told a different story. Drought had drained the lake to levels that exposed ancient tree stumps along the shoreline. Boat ramps sat useless, ending dozens of feet from the receding water. Marina owners watched their businesses wither. Climate scientists warned California's water crisis might never fully recover. Then, everything changed. Beginning in late 2022, atmospheric rivers slammed into the Sierra Nevada with unprecedented intensity. By midwinter, monitoring stations recorded snowpack levels of 237% of normal. When spring arrived, billions of gallons poured down mountainsides faster than hydrologists had predicted. The lake rose 4 feet in a single season. Water managers opened dam gates at the Truckee River outlet to maximum legal flows. It wasn't enough. By early 2024, Lake Tahoe reached levels not seen since 2019. Tourism officials celebrated. Headlines proclaimed California's water miracle. But while the public celebrated, scientists noticed something else. Seismographs began recording anomalies: small tremors, subtle shifts, patterns demanding attention. The drought was over, but something was waking up far below that pristine surface. Beneath Lake Tahoe's surface runs one of California's most dangerous secrets: the West Tahoe Fault. This massive geological fracture extends approximately 25 miles directly under the lakebed. Scientists have monitored it for decades, and what they've learned keeps them awake at night. This fault is capable of generating earthquakes up to magnitude 7.3. To understand what that means, consider the 1989 Loma Prieta earthquake that devastated the San Francisco Bay Area. That quake measured 6.9 and killed 63 people. A magnitude 7.3 releases approximately 2.5 times more energy. The destruction would be catastrophic, but the magnitude isn't what terrifies geologists most. It's the timeline. Research teams from the University of Nevada and USGS have spent years analyzing sediment cores from the lake bottom. Their findings are alarming. The West Tahoe Fault last ruptured approximately 4,000 years ago. Based on the fault's slip rate and accumulated strain, it's now overdue for another major event. The fault system isn't even a single clean fracture. It's a complex network of interconnected segments that could rupture together in a cascading failure. This fault receives a fraction of the attention given to the San Andreas. No Hollywood movies dramatize its threat. Few tourists know they're swimming above a ticking time bomb. Yet seismologists place the Tahoe Basin among California's most concerning regions. And now billions of tons of water sit at maximum capacity directly above this overdue fault. Water seems harmless until you calculate the scale. A single cubic foot weighs 62 pounds. Lake Tahoe at maximum capacity holds approximately 39 trillion gallons. Every second, billions of tons of pressure push down on the lakebed with relentless force. This weight doesn't rest on solid ground. It presses against fractured bedrock, infiltrating cracks and fissures. When that weight sits above an active fault system already stressed by tectonic forces, It creates conditions documented triggering earthquakes worldwide. The phenomenon is called induced seismicity. In 1967, India's Koyna Dam reservoir triggered a magnitude 6.3 earthquake that killed 180 people. Lake Mead has generated hundreds of small earthquakes since the 1930s. China's Zipingpu Reservoir may have contributed to the 2008 Sichuan earthquake that killed nearly 70,000 people. Water triggers earthquakes through two mechanisms. First, the sheer weight adds vertical pressure to fault systems already under horizontal stress. Second, more insidiously, water seeps into rock fractures and increases pore pressure, reducing the friction that keeps fault surfaces locked together. It lubricates the fault plane, making it easier for accumulated strain to release suddenly. Lake Tahoe now sits at maximum capacity, all of it bearing down on a fault that has been accumulating strain for 4,000 years, far longer than its typical rupture cycle. Seismic monitoring stations around Lake Tahoe have detected a disturbing pattern. Small earthquakes are increasing in frequency along the West Tahoe fault system. Magnitude 1.9 tremors have been recorded in recent months, too small for humans to feel, but the instruments miss nothing. These small events are potential precursors, warning shots from a fault system under increasing stress. Before many major earthquakes, fault systems exhibit increased micro-seismic activity. The 2011 Tahoe earthquake that devastated Japan was preceded by increased smaller earthquakes in the weeks before the magnitude 9.0 main shock. Monitoring stations now operate around the clock. University researchers and USGS scientists analyze every tremor, mapping locations and measuring depths. Activity levels that would have seemed normal 5 years ago now appear elevated against the backdrop of maximum water pressure. The challenge is interpretation. Earthquake prediction remains one of science's most elusive goals. Small tremors might indicate an imminent rupture, might release enough strain to delay a larger event, or might mean nothing at all. What scientists can say with certainty, the combination of factors at Lake Tahoe, an overdue fault, maximum water load, increasing seismic activity, demands vigilance. If the West Tahoe fault ruptures at maximum capacity, the earthquake will only be the opening act. Lake Tahoe's underwater terrain plunges to depths exceeding 1,600 feet, with near-vertical walls in some areas. Clinging to these steep underwater cliffs are massive slopes of loose sediment, millions of tons accumulated over millennia. A magnitude 7.3 earthquake would shake these formations violently. Scientists believe the result would be catastrophic underwater landslides occurring simultaneously. Millions of tons of sediment would collapse into the lake's depths. When that much material displaces that much water that quickly, physics takes over. A tsunami forms. This isn't speculation. Geological evidence proves it happened before. The McKinney Bay landslide moved approximately 12 cubic miles of material in a single ancient catastrophe. Modern modeling projects waves potentially reaching 30 feet high, traveling at speeds approaching 100 miles per hour. What makes these underwater landslides particularly dangerous is their unpredictability and scale. Unlike coastal tsunamis triggered by offshore earthquakes where the epicenter is distant from shore, Lake Tahoe's landslides would occur directly adjacent to populated shorelines. Some communities sit less than a mile from underwater slopes that hold millions of cubic yards of unstable sediment. When these slopes fail, there's no buffer zone, no shallow continental shelf to dissipate energy. The waves would form essentially at the doorstep of residential neighborhoods. Computer simulations show that in certain worst-case scenarios, multiple landslides triggering simultaneously around the lake could create a chaotic pattern of converging waves, amplifying their destructive power in specific locations where wave energy concentrates. The geography makes it deadly. The lake is only 12 miles wide at its broadest point. A tsunami generated on one side reaches the opposite shore in minutes. Ocean tsunamis give coastal populations hours to evacuate. Lake Tahoe offers no such luxury. Communities would feel the ground shaking and watch the wave approaching within the same terrible minutes. The enclosed basin creates another nightmare. Unlike ocean tsunamis that dissipate across open water, a lake tsunami reflects off the surrounding shoreline. Waves bounce back and forth, striking communities multiple times. The initial wave is only the first assault. Approximately 55,000 people live in the Lake Tahoe Basin year-round, but during peak summer weekends, over 100,000 visitors pour into the area. During ski season, casinos and resorts pack with thousands more. On holiday weekends, the population can triple. All of these people would have mere minutes to respond to a tsunami most don't know is possible. The geography creates a deadly trap. Lake Tahoe sits in a mountain basin accessible by a handful of two-lane highways. During normal summer traffic, these roads jam with vacationers. During a mass evacuation, they would become parking lots. Emergency management faces a jurisdictional nightmare. The lake straddles California and Nevada. 5 counties share responsibility for shoreline communities. 2 state governments, multiple fire districts. Dozens of local agencies would need to coordinate instantly during a crisis that unfolds in minutes. Property values along the shoreline exceed $15 billion. Luxury homes, historic resorts, marinas, commercial districts, all built on the assumption that the serene blue water poses no threat beyond standard California seismic risk. Most residents move to Tahoe for beauty and tranquility. Few realize they've built their lives above a fault waiting 4,000 years to move. Communities along the Pacific coast have tsunami sirens, established evacuation routes, and public education campaigns. Lake Tahoe has none of this. No sirens line the shoreline. No clearly marked evacuation routes exist. No awareness campaigns warn residents about the fault beneath their feet. Most people who live in the Tahoe Basin understand they're in California earthquake country, but few have any idea they face a tsunami threat in an alpine lake 6,000 feet above sea level. Most will never read the scientific papers documenting the West Tahoe Fault's history. They'll learn about the threat when the ground begins to shake. The coordination challenges are severe. During a disaster that unfolds in minutes, agencies would need to coordinate evacuation routes and emergency services across state lines while dealing with collapsed buildings and failed communication systems. Even emergency services could become casualties. Hospitals damaged by the earthquake. Fire stations flooded by the tsunami. Modern seismic networks detect earthquakes too small to feel. GPS stations measure ground deformation down to millimeters. Satellite imagery spots surface changes invisible to the human eye. Yet despite all this technology, one fundamental limitation remains. Earthquakes cannot be predicted. Scientists can identify faults, calculate probabilities, and recognize warning signs. What they cannot do is tell you when a specific fault will rupture. The Earth doesn't announce its intentions. A fault can remain locked for centuries beyond its average rupture interval or fail tomorrow. Research teams continue their work in the Tahoe Basin. University seismologists analyze tremor patterns. USGS scientists refine hazard models. Graduate students examine sediment cores. Funding remains a struggle. The West Tahoe Fault hasn't ruptured in living memory, so it doesn't generate headlines or justify large research budgets. Yet the expert consensus is unambiguous. The West Tahoe Fault will rupture. This is geological certainty. Faults that accumulate strain eventually release it. That pressure will find release. The only questions are when and how violently. To understand what communities around Lake Tahoe face, we need to walk through the nightmare scenario step by step. Because this isn't an abstract threat, this is a sequence of events that could unfold on any given day, transforming paradise into catastrophe in minutes. It would likely start on an ordinary morning, tourists having breakfast at lakeside restaurants, families packing beach bags, workers commuting to South Lake Tahoe, the lake reflecting the Sierra Peaks in that impossibly perfect blue. Nothing would seem different. Then the ground would begin to shake, not gentle rolling motion, but violent, sharp jolts, the signature of a shallow rupture happening almost directly beneath your feet. Buildings would sway, windows would shatter. The shaking would last 30 to 45 seconds, though it would feel like an eternity. This is a magnitude 7.3 earthquake, and the energy released would be equivalent to detonating multiple nuclear weapons. But here's where Lake Tahoe's situation becomes uniquely terrifying. As the ground shakes, those massive underwater sediment slopes, the ones clinging to near vertical walls dropping 1,600 feet, would begin to fail. Millions of tons of sediment would start sliding simultaneously from multiple locations around the lake. The underwater avalanches would be invisible to people on shore. But the effect would be immediate. The displaced water would have nowhere to go but up and outward. Within seconds, waves would begin forming, not gentle swells, but walls of water, 20 to 30 feet high, moving at speeds approaching 100 miles per hour. People on shore, still reeling from the earthquake, would have perhaps 2 to 3 minutes before the first wave struck. That's not enough time to reach high ground. It's barely enough time to realize what's happening. The first wave would hit with the force of a moving freight train. It would surge inland, destroying everything in its path: homes, businesses, cars, trees, people. The water would carry debris, boats torn from marinas, pieces of destroyed buildings, vehicles, turning each object into a battering ram. The wave would penetrate hundreds of feet inland in low-lying areas. But the first wave wouldn't be the end. Because Lake Tahoe is an enclosed basin, the water would reflect off the surrounding shoreline and bounce back. A second wave would form and strike within 10 to 15 minutes. Then a third. Each wave would crash into communities trying to rescue survivors from the previous impact. Meanwhile, fires would likely be breaking out. Ruptured gas lines ignited by sparks, overturned vehicles, damaged electrical systems. The same earthquake that triggered the tsunami would have compromised fire suppression systems and blocked roads. This was exactly what happened in the 1906 San Francisco earthquake and the 2011 Japan tsunami. The fires became as deadly as the initial disaster. The two-lane highways would be clogged with panicked evacuees, damaged by the earthquake, and potentially flooded by tsunami waves. Helicopters would become the primary means of rescue, but there are only so many available. Thousands would be stranded, injured, and terrified with help hours or days away. This scenario isn't speculation. It's what the physics and geology tell us would happen. Scientists have modeled it. Emergency planners have mapped it. The only unknown is when. Lake Tahoe represents one piece of California's seismic puzzle, but it illuminates broader concerns. While the San Andreas gets the attention, California is crisscrossed with capable faults: the Hayward, the Calaveras, the Garlock. Each represents significant threats to specific regions. The connection between water infrastructure and seismic risk extends beyond Lake Tahoe. California's water system includes numerous large reservoirs near active faults: Shasta Lake, Oroville Reservoir, Castaic Lake. Each represents a similar equation: massive water weight on fractured bedrock. Climate change adds complexity. As California's weather becomes more extreme, longer droughts followed by more intense atmospheric rivers, water bodies will experience dramatic fluctuations. These rapid changes in water load could affect fault stability in ways scientists are only beginning to understand. California's earthquake preparedness has focused on the highest-profile threats, but Lake Tahoe reveals that catastrophic earthquakes could emerge from unexpected sources. Faults most residents have never heard of, in locations where few expect major seismic events. Lake Tahoe stretches across the Sierra Nevada like a mirror of impossible blue, reflecting mountain peaks so perfectly that photographs barely seem real. Visitors arrive by the millions. They photograph sunsets and post images celebrating paradise found. They see beauty, tranquility, escape. What they don't see is the truth beneath the surface. The water reads 6,229 feet, maximum capacity. Billions of tons pressing on bedrock fractured for millennia. After 5 years of drought, atmospheric rivers delivered what seemed like a miracle. But scientists see maximum water load pressing on an overdue fault. They see increased micro-seismic activity. They see all the elements of induced seismicity aligning, the same conditions that triggered disasters at reservoirs worldwide. Daily life continues as if none of this matters. The 55,000 permanent residents go about their lives. Millions of visitors arrive seeking escape. They swim in crystal-clear water. They boat across the surface. They build luxury homes along the shoreline. Children build sand castles above a fault that hasn't moved in 4,000 years, but will move again. The instruments keep recording. Scientists keep analyzing. The small earthquakes keep coming. Whispers from deep below that might mean everything or nothing. The Earth doesn't announce its intentions, but the physics doesn't care about human denial. Strain that accumulates must eventually release. The West Tahoe Fault has been patient for 4,000 years. It has waited while humans discovered agriculture, built civilizations, and developed the technology to detect its presence. It will continue waiting for as long as it takes. And then, on a day that will seem like any other day, the patience will end. The rock will fail. The strain will release in seconds. And everyone who dismissed the warnings will understand that the mirror was always lying. If you live in or visit the Lake Tahoe Basin, this information cannot stay hidden. Share this with your community. Talk to local officials about emergency preparedness. Demand better warning systems and evacuation infrastructure. Sign up for earthquake alerts through the USGS Shake Alert system. Make sure your family has an evacuation plan that accounts for both earthquakes and tsunamis. Knowledge is the first step toward survival. You now know what most visitors and many residents don't. Lake Tahoe sits on a geological time bomb, and with the lake at maximum capacity and seismic activity increasing, conditions have never been more concerning. What will you do with this knowledge? Drop your thoughts in the comments below. Have you visited Lake Tahoe not knowing about the West Tahoe Fault? Do you live in the basin? And if this video opened your eyes to a danger you didn't know existed, hit that subscribe button. Because the Earth doesn't stop moving just because we stop paying attention. The fault beneath America's most beautiful lake has been waiting 4,000 years. How much longer do we have?